Hi friends, have a great day. This is page number 43. First question: how do CFBs make fuel flexibility compatible with low emissions? Answer: CFB boiler inherently produce low NOx emissions than other boiler designs, while SO2 and other acid gases are absorbed during combustion by adding a suitable sorbent. CFB combustor burn fuel in a turbulent atmosphere under relatively uniform mixing conditions to achieve efficient combustion with low NOx and CO emissions. Inasmuch as they operate at lower leverage furnace temperatures, 1090 degree to 1200 Kelvin, compared to Stoker and PC fired units. They lend for ammonia and urea injection in a better way in case additional NOx control is required. CFP boilers keep SO2 emissions at bay since the combustion temperature is within the range where the reaction of limestone with SO2 liberated during combustion is ideal. According to one recent report, 90% of SO2 removal is routinely achieved with CAS ratio of 2:1 in CFB combustors. A survey of several operating units reveals that they all achieve very low levels of SOx, NOx, and fly ash emissions, generally well below permitted values, with little difficulty. One of the world's largest peat-fired CFB boiler is operating in a Sinjoki, Finland, at a paper mill. Designed to fire a mixture of peat, wood waste, coal, and paper mill sludge, it is one of the largest clean CFB units designed to date. Thanks to inherently low NOx emission capability of circulating fluid-acid bed combustors while burning fuels of varied characteristics. And in this table, we can see the emissions performance for several CFB units. Included ammonia injection system for NOx control 2 unit is described as a hybrid bubbling bed CFB. 3. Calcium to sulfur ratio is 1.8 to 2.1. Source Electrical Power International, September 94. Reported with kind permission of Alstrom Pyro Power Incorporation, San Diego, USA. So these are the tablet. We can see the NOx, SOx, CO, fly ash value for each different capacity boiler. In here, the actual is grade slightly compared with permit is lower and higher. So we can see in the table. The next question: do the CFB combustor ban only solid fuels? Answer is no. Solid, liquid, or gaseous fuel or fuels are burned together with inert materials like sand, silica, alumina, or ash, and or sorbent such as a limestone. Question: how is the process realized? Answer: the charge of fuel, sorbent plus inerts are kept suspended in furnace through the action of the primary air distributor below the combustor floor. Secondary air may be introduced into combustor to provide a staged combustion effect. As the combustion takes place, the generated heat is transferred from the hot bed material to the membrane water wall. Next question: what makes CFB technology an attractive proportion in comparison to other firing techniques? Answer: this is described to the 3 T's of combustion: time, turbulence, temperature. Fluidization promotes intensive turbulence and the entire mass of solids behavior, much like a liquid. Improved mixing generates heat at substantially lower temperature, 1080 degree Kelvin to 1175 degree Kelvin, and gives rise to more uniform temperature distribution in the furnace space than a stoker fire unit or a PC unit. Therefore, a properly sized combustion chamber will release heat at an equivalent level of a convection boiler, but a lower temperature and theoretically without any loss in efficiency. The added turbulence budgets several advantages: less volatilization of alkali compounds, to reduce chance of hot spots on boiler and shell surfaces, 3 less sensitivity of fuel, 4 a smaller furnace volume. Extra volume is not required to allow the ash to cool before flowing through the convective passes. Low combustion temperature offer advantages for emission control. Operating lamps are well below the formation point of thermal NOx. Stacked combustion is feasible by introducing secondary air to minimize fuel-bound NOx formation. Addition of a suitable solvent elements or at least minimizes the need for downstream control. Sulfur absorption reactions are thermally balanced by the operating temperature range of CFB units. Thus, there tends to be designed trade-offs involved in maintenance high SOx removal efficiency together with high combustion efficiency. Another major advantage of lower combustion temperature, particularly when fired coal, is realized through the minimum stagging and fouling and other problems associated with PC fired and stoker fired units. The next question: SO2 removal by sorbent absorption. CaO plus SO2 plus of O2 gives CaSO4 is thermally balanced over the operating temperature range of CFB combustors. How is the optimum absorption of sulfur influenced by the CFB combustion temperature? Sulfur dioxide is absorbed by lime and reversible reaction. CaO plus SO2 plus of O2 gives CaSO4 plus 486 kg per gram mole, which becomes counteroperative as the temperature increases. However, optimum absorption of sulfur dioxide is achievable at high CFB combustor temperatures provided higher sorbent injection is made, means at higher calcium to sulfur ratio. How is steaming rate controlled in CFB units? Answers: steaming rate is controlled by manipulating four primary bed temperatures: bed height, bed temperature, solid inventory, superficial gas velocity. Velocity changes accomplish most of control. For instance, reducing the fluidation velocity, less heat transfer surface is exposed to the bed. When airflow is shut off completely, heat transfer drops particularly to zero, offering quick Turn down capacity. Turn down and steam rate control can also be affected by reducing the quantum of bed inventory, means bed material, or regulating fuel feed, as with firing system, other firing system. In this diagram, we can see the optimum absorption of sulfur by calcium is achieved at normal CFB combustion temperature. Source is Electrical Power International, reproduced with kind permission of Alstom Pyropower Incorporation, San Diego, USA. The bed temperature and calcium sulfur molar ratio. When the bed temperature is low, from this graph we can see when the bed temperature is low, CAS ratio is smaller. From increases of the bed temperature, the CAS molar ratio is higher. So the next question: what is pyroflow CFB technology? Answer: pyroflow is the patent trademark of famous Finnish co Alstom Pyropower, recognized worldwide as the leader in the supply of fluidized bed combustion system. Note: Pyre is the Greek word for fire, and flow means movement or circulation. Hence, pyroflow system is true representative of circulating fluidized bed combustion. Thank you. We will see the next video further. This is page number 45.